Good morning, everybody. I know that usually in the beginning of the semester, we have a lot of attendance for the live audience, live sessions, but because we're recording this class, it seems like everybody is relying on that recording. It's still very, very important that you guys attend lecture, because if in case you have questions, they're answered better when they're actually done live. So that's why it's very important that you guys attend and hopefully answer all of your concerns and discuss the problems and do things like that. It's still, you have assignments that are due based on either attending live or actually watching the recording later. So it's still your job to do that. We are in chapter 16. We started a little bit of chapter 16, so we're going to finish it today. Wednesday, we will have dedicate it to problems from this chapter, namely dealing with basically the Doppler effect and probably also the beats and things of this nature for sound. And the big deal from this chapter is going to be actually the Doppler effect. So hopefully you guys will focus on that as much as possible, because it has implications and applications in a lot of different areas in physics, astronomy, and even in other fields of science, okay? The other thing also is that this afternoon we still have lab. It's scheduled. It's going to be discussing the standing waves, which is a concept that we discovered for the string. So we're going to be doing it actually for the string. But again, standing waves have applications in almost every single branch of physics because of the fact that it's a resonance phenomenon, where basically you have a sustained, if you wish, pattern that is exhibited by these waves, okay? Later on, when you take physics 4D, you will learn more about this when you study, for example, the hydrogen atom. And one of the explanations for the hydrogen atom relies on this idea of standing waves. But standing waves in their own, they have importance. That's why we'll be discovering them later on in the lab. So Harris, you just joined us. Basically, what we were saying is the fact that we will be doing, finishing the chapter today, and starting and doing the problems on Wednesday. We will finish chapter 16. By Monday of next week, we will start chapter 17, which deals with thermodynamics. And again, the lab this afternoon is standing waves. And on Monday of next week, the lab is actually going to be on calorimetry, or the introduction to thermal physics. Basically, that's what the title of the lab is. The lab after that is going to be heavily in basically dealing with engines, okay, thermal engines and so on and so forth. Please do not think that thermodynamics, which is the next big deal, is related somehow. I know we're going to be doing PV equal to nRT, and some of you have seen that in chemistry. You're going to see it from the physics perspective, and it's actually the foundation of what you saw in chemistry, number one. But number two, we're not going to be doing any chemistry whatsoever in this class. So do not think that we're going to be repeating what you guys did in chemistry. So this is going to be a thermodynamics in its full glory, one of its applications in chemistry that you saw already, but that's not what we're doing in chemistry, so that you guys have an understanding. I know a lot of my students, when they see the title, they think, hey, let's maybe just like what we did in chemistry, so maybe we'll just skip over it. But then when they see the level of physics that is involved in it and the amount of work that is involved with it, they immediately basically reconsider that assumption. So again, please pay attention to all of these things, because it's really supposed to be the foundation for a lot of other things. Again, whether in engineering or physics or chemistry or biology or the other applications, that's basically what we'll be doing in, later on. But let's finish sound first, okay? So let me share with you the screen. So this is what we talked about briefly last time, basically the fact that the sound, I know I'm not going to derive this expression, and I have hopefully alluded to the fact that it's on chapter 47 from the book by Feynman and Feynman Lectures. And Feynman Lectures are free resource. So basically you can, any point in time, you can always look at them, and they have you can access them online. He has 3 volumes, and I have all of the 3 volumes in here. And if you happen to get your hands on the written materials, they're actually outstanding materials for teaching physics, for learning physics, I should say. And they're accessible online through Caltech, and I already gave the link in my syllabus. Always in my syllabi, I put the link for them because they from time to time I refer to them. And this is no different. So chapter 47, CH47, will give you a detailed, basically, derivation for the wave equation. It's going to look like this. It's going to go, he uses actually chi, the displacement of the mass of the air, due to sound, due to a disturbance to sound, and basically derived in a wave equation that looks like the second derivative of chi with respect to time, where chi is actually this displacement. We're kind of short of basically symbols. That's why you use chi, because again, this is a wave that displaces in the same direction as the disturbance is. So it's like Slinky, except I don't have the Slinky ready. Think of this one as where the wave is traveling, and in the same, that's where the disturbance is. So we create a disturbance and you let go of it. Obviously, the disturbance in this case travels. Obviously, this is a string, not a, now I'm creating actual disturbance in it, okay? If you happen to see that, that is exactly, there is a compression followed by an elongation, compression, elongation, and so on and so forth. Or for the case of sound, it's called compression and rarefication, okay? So the material at some point, basically there is more of it and then relaxes, more of it relaxes, and so on and so forth. And it travels along the same direction where the disturbance is, hence the word longitudinal waves, because of the fact that the waves are along the same direction where they're traveling. And like the waves on the string, which we saw them as being transverse waves, okay? So these are not transverse waves. Sometimes they're called compressional waves because indeed in space, they're actually, sound travels in all directions around you. So even if you are behind the source, you could still hear sound, unless it has that shape there for a microphone that help it basically in a unidirectional motion. Otherwise, sound is actually going in a sphere, okay? And as it travels further and further, the intensity of sound drops with the distance further and further, basically. And this phenomenon is true for all kinds of waves. It drops like 1 over distance squared because whatever disturbance that causes it immediately near the source is intense. As you move further and further away from it, that intensity basically spreads over a bigger and bigger sphere. So it's going to drop like this, the area of the sphere. And the area of the sphere is 4 pi r squared. So the intensity must drop like 1 over distance squared, which is 1 over meter squared. As a matter of fact, if you are very far away from the source, you're not going to hear anything, despite of the fact that the source is still producing sound, probably the same intensity. So in this case, the effects of the distance are important when it comes to sound. And it comes to all kinds of waves, by the way, okay? Because they spread over space. In the case of the one-dimensional wave on the string, we don't notice that because we're assuming there is no damping. And actually the experiment that you're going to be doing later on today for the standing waves, you can control that parameter. What damping does is basically how the wave is basically, the energy of the wave is consumed along the way, okay? And this is due to all kinds of phenomena, including friction, including the air resistance, including all of the other phenomena. You guys have seen chapter 14. I know we didn't do chapter 14 in this class, but you did it on your own with your class when you were in physics 4A. And chapter 14 had oscillations in it, not waves, which are localized basically disturbances. And the localized disturbance also, you had the same phenomenon. Namely, if I take this mass attached to a spring and disturb it from its equilibrium, yes, the mass is going to oscillate, but I notice that the oscillation starts to become less and less over time because of friction, okay? Until at some point the mass will stop, okay? So in this case, that is the damping. That is the phenomenon where the energy is lost to the system. Unless, of course, you have a force that keeps on pumping energy to the system. In other words, for example, if you take the mass around the spring and start moving it and don't let go, in this case, you have a forced oscillation, okay? So even though there is damping still, but it's still moving because the cause of the disturbance is still there, namely the force that caused the motion to be there. An interesting case that you saw also in chapter 14, and it's true also here in this case too, is when the oscillation, the forced frequency, basically, how often do you go back and forth, is in sync with the natural frequency of that mass spring system. You have what is called an oscillation. In other words, you're going to help it move further and further each time. The amount of energy you're adding each time is the same, but because it's in sync, that's going to add to the system, and the system will be in forced oscillation that is in resonance with the external disturbance, with the force that causes that disturbance. And of course, the oscillations will become higher and higher in amplitude until at some point the system cannot sustain it anymore and breaks apart and falls apart. So that is what the importance of resonance. The same thing when mass on the string, when you create waves on it, and the wave goes to the other side and is reflected, and if the frequency of what causes that is actually in sync with the geometry, basically the wavelength in this case is related to the length of that string. If there is that relationship where lambda is either twice the length, or the length itself, or 2/3 of the length, or 4/2 of not 2/3, 3/2 of the length, I'm sorry, or 4/2 of the length, or 5/2 of the length, or 6/2 of the length, anyway, an integer multiple of the length divided by 2, then in this case we have resonance. Okay, we have standing waves. This is similar in a sense to chapter 14. This is the similarity between chapter 14 and chapter 15. And as a matter of fact, we're going to see it also here in the case of sound too. So this resonance exists everywhere. Okay, so this is in a nutshell connection between all of the other ideas. So I'm hoping that you guys will go, please ignore the derivation that is in the book. I hate it. Okay, that's why I'm skipping it, because it really doesn't talk about the physics of the waves in this case and what's going on in them and all of that. As a matter of fact, in the lab, I was tempted to do the derivation and give it to you guys so that you see it. But because it's a little bit involves a lot of stuff, so again, I refrain from it. There is actually derivation that involves sound and how it travels in solids, and that goes back to chapter 14 from you guys' lecture, where you take each molecule, each particle, doesn't matter what it is, of the solid, atom or molecule or whatever, and attach to its neighbor with what looks like a spring, and then those disturbances travel in the solid, and that gives the same equation that we are having there. So I was going to be tempted to do one or the other, but then again, they're afraid because it's really a complication that we really don't need. Anyway, we saw it in the string. If you are curious trying to see it in the sound, I have here chapter 47 from Feynman lectures. If you want to be satisfied to some extent with the derivation in the book, go for it, but that's not really the actual physics, because it works its way backward trying to find this equation. Once we find it, we find that the sound, in the case of solids, it behaves like this one, square root of the bulk modulus, which again, you should have seen when you did elasticity in physics 4a, or Young modulus, okay? This is the bulk waves, or Young modulus in the case of the solids, I'm sorry. And I also going to write it in terms of temperature for the case of gas, for an ideal gas, okay? You're asking what in the world is an ideal gas? Hold on. CH17 and 18, okay? Chapters, the next two chapters, okay? Ideal gas. Well, we find that the velocity in this case is proportional to a factor, which I'm going to write right now. R, you're familiar with it, which is just, if you took chemistry, it's the same constant for the ideal gas. T is a temperature in Kelvin, divided in this case by M, where M is the molar mass, okay, of the gas. So this expression is a bunch of things in it. So this is just to compare it to the other expression for the velocity as a function of temperature. So it's clear in here that is proportional to the temperature, but this temperature is not in Celsius. This temperature is in Kelvin. So let me rewrite this expression again, because sometimes it's kind of so the velocity of sound in an ideal gas that means it's air. If it's rarefied enough, it's not too much density in it, so it has some meets basic conditions for it to be ideal gas. An ideal gas obeys the law that you probably heard of it called the PV equal to nRT. Its pressure, its volume are equal to a certain number, which is the number of moles in this case, times R, and R is just a constant, 8.314, times T, and T is in Kelvin. This T is not in Fahrenheit, it's not in degrees Celsius, but it's in Kelvin. And Kelvin has a specific starting point where basically all matter freezes at negative 273.15 degrees Celsius, okay? So this T cannot be equal to 0. 0 Kelvin doesn't exist. It's just a hypothetical value. T is always positive. That's why the velocity of sound, no matter what, it's going to be proportional to this temperature T divided by specific property of the gas itself, which is molar mass. Here, the molar mass is actually in kilogram. Typically, the molar mass is in grams. And whatever that number on the periodic table, just add to it a gram. But we're going to convert that to a kilogram to find the velocity that is in meter per second, because this R is 8.1314 joules per Kelvin, okay, basically per mole also. Gamma is something that is going to be complicated to explain at this point, but believe me, before the end of chapter 19, you will know exactly what that is, okay? So gamma is the ratio of the specific heat at constant pressure versus the specific heat at constant volume. So at this point, don't care about the expression. The whole deal about this expression is the velocity of sound is proportional to temperature in Kelvin. That is the key. In general, we write it approximately to be the velocity of sound at room temperature times roughly 1 plus 1/2 of delta T over T, okay? T naught, okay? This is room temperature, about 273 plus, about 300 Kelvin. Roughly this number, okay? If it's not given to you, and it's going to be given to you in all of the problems, take the speed of sound to be 343 meters per second. If not given. So for you, you don't care about anything else, okay? The velocity of sound from now on is 343 meters per second until we see later on exactly what's going on. This gamma in here, there was actually a debate in the whether or not the sound involves constant temperature or something else, and the expression that Mr. Newton came up with was wrong. So later on, it turns out sound travels without exchange of heat, which is so rapid that it's there is not enough time for heat to be exchanged. That's why this factor of gamma came in. So that's just in a nutshell. So the process in this case is at constant heat, or no heat exchange, I should say. There's no such a thing, constant heat, no heat exchange, and that is a process that we're going to learn later on about it, and it's called the adiabatic process. If you have seen it in chemistry, you have a head start. If not, don't worry, it's no big deal. We're going to see it in chapter, I believe, 18 or 19, one of the two, okay? So the bottom line is, for me, physics 4C, I'm in chapter 16 right now. What is the speed of sound? Unless it's not given, this is the number you're going to be taking it for the air, okay? They're going to assume it's room temperature and work with it, unless they tell you, oh, sound in this temperature is traveling with this one, or in this medium is traveling with that one. So from that on, you're going to change your problem. You're going to use that value that was given to you. Is this clear? So this is item 1 for the discussion. Use the value. If you're not sure, you don't remember, use 340. If you don't remember the 3 there, is it 3 or a 2 or? I remember it's 300 and something, as long as you remember 340. 43 is better. Good? Item 1. Are we good on this? Okay, I see you guys writing. When you guys write, I can't see this thing because... Okay, very good. At least I have a couple of confirmations in here. So that's the bottom line from all of this so far, okay? And it's a wave equation, and this is the sound for it. Now the velocity for it, I'm sorry, for the wave. Now, we talked also about the intensity and the fact that the intensity is proportional to the amplitude of the oscillations, because if I create a disturbance, how big it is, how small it is. So it's always square of that number, of course, proportional to the velocity v that we came up with. That's basically what we found. It's proportional to the frequency squared. And the ear has this tendency. We humans can hear only certain sounds of a given frequency all the way to a maximum from, what is it, a 20 hertz all the way to like 20 kilohertz, 20,000 hertz. Okay, so that is the range of frequencies that we can hear. Obviously, young people can hear very high frequencies, and as you get older and older in age, those frequencies start the eardrum starts to basically be less and less sensitive to those high frequencies, and your range is limited. As a matter of fact, even for normal people during normal age, their range is actually not that one. That is actually a hypothetical limit between the lower and the higher frequencies. Low frequency is what, like, for example, elephants and whales use for their communications. High frequencies, for example, where bats use to go around basically their environment. They use extremely high frequencies that we cannot hear. And that is basically the communication. As a matter of fact, even whales and elephants, they use super low frequency that they could be screaming at one another and we cannot hear it. The advantage of low frequencies is they travel very long distances, but they sound very deep in voice versus those that are very sharp, if you want to compare the high to the low frequency. They're called actually pitch, okay? So the word used for sound is pitch, and I think this is one of the questions that you're going to be asked for during the quiz. So pitch is what is referred to as frequency, the way that the ear perceives sound, basically. The other thing also is the intensity of the wave, of the sound. If the sound is below a certain intensity, if you are very, very far away from it, or even if you are very close from it, but the intensity drops below 10 to the negative 12 watts per meter squared, you're not going to hear it. So this is the threshold of hearing. When the intensity becomes at 1 watt per, so this is the threshold, when the intensity is equal to I naught. When the intensity is equal to 10 to the power 0, namely 1 watt per meter squared, this is actually the threshold of pain. Okay, if you go to a concert, that's probably the intensity with which they are broadcasting, especially if you are next to the loudspeakers. Okay, you're going to be really, 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 I mean, your ear is going to hurt. It's probably going to start to rupture. You have to be very careful in there. So it's not only the frequency, but it's also the intensity of the wave and how far and close you are from it. Obviously, you guys see that this range is huge, between 1 or 10 to the power 0 to 10 to the negative 11 and negative 12. That is a huge range. I mean, we cannot really use that number. So that's why we use the symbol beta for this one, for the intensity. And the symbol beta is just a logarithmic scale, because just to give us a sense of basically a range with which we can deal. So if I say beta equals to 0, for example, I mean it's a threshold basically of sound. Basically, if beta is equal to a certain limit, let's say for example 120, that is the threshold of pain. So the definition is the following. First of all, 10, and this is the intensity level okay, in decibels. Okay, we have somebody's cooking in there. That's why this beeping sound. Sorry about it. Okay, so we have 10 decibels times the log in the base of 10. This has to be clear that this is in the base of 10. Hold on, let me stop the sound quickly in here and see if I can fix this. Sorry about that. Anyway, so in the base of 10, not in the base of not in the natural log, okay? So if we are in there, so again, the ratio of the intensity of that sound with respect to the ratio of the intensity of the threshold of hearing. So for example, if beta is equal to, let's say for example, let's go back into this one, the threshold of pain. Threshold of pain. By the way, this is something that is you might have as a homework problem and assignment. So you really need to know how to use that. So again, if I is equal to 1 watt per meter squared, that means beta in this case is going to be 10 decibels, of course, times the log in the base of 10 of 1 over 10 to the negative 12, okay? Again, the watt per meter squared and the watt per meter squared cancel. And this is, as duly noted, it has to be dimensionless inside the argument of the log. And log of 1 is 0, and log of 10 to the negative 12 is negative 12. So this is basically is going to be 10 in decibels, of course, times, of course, if you guys remember the relationship of the log of the ratio is the log of the numerator minus the log of the denominator. And the advantage of writing it this way is, first of all, this is 0, and this is negative 12. Don't forget you have a negative in here times a negative, so it brings it to a positive number. So beta is positive 12 times 10, which is exactly the unit I was referring to, 120 decibels, okay? So this is the same intensity, but expressed in the intensity level units, which is in decibels, to tell me that, hey, if you hear 120 decibels, that means it's really, 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 really loud. You're very close from the source, okay? If you are at beta equals to 0, barely, you're not going to hear anything because 10 to the negative 12 over 10 to the negative 12 is 1 and log of 1 is 0. So beta is equal to 0. So beta now is a nice scale to write with. So if beta is 0 and all the way to beta, so this is I in decibels now, okay? Then obviously if we're in this scale in here, this is the onset of hearing, okay? So this is barely hearing. You are in here, this is pain. And anywhere in between is a number, okay? So let's say, for example, you have an 80 decibels, which is the normal conversation that we do, okay? 80 decibels. So the intensity in decibels is 80 decibels. So what is that in terms of power? So if I go back to the expression, I write 80 equals to 10 log in the base of 10 of I over 10 to the negative 12. If I try to find I in this case, I have to erase everything. So by the way, 80 divided by 10 is just 8. So 8 is log in this case of I over 10 to the negative 12. That means that I to the I itself is equal to 10 to the negative 12 times 10 to the power 8, okay? And if I work out my algebra correctly, that is 10 to the negative 4 watts per meter squared, okay? Or 0.00 watts per meter squared. And let's say, for example, the station itself is actually broadcasting super high. Let's say, for example, broadcasting at, I'm just going to throw a number in this case, at, let's say, for example, 5 watts per meter squared, which is a very intense wave in this case, okay? So this is the actual source, okay? So this is the source of the wave. I want to know how far I'm going to need to be from it to hear just 80 decibels, okay? So this is super intense. This is way above the threshold of pain, okay? It's somewhere in here. It's probably 121 decibels or something, okay? So if I use this expression correctly. So how far do I need to be? So in this case, I know that this one is spreading over a sphere. So by the time it reaches this distance r, the same intensity is going to be I, now where I am hearing it, is equal to this I of the source, but now it's spread, I'm sorry, 5 watts. Spreading, it's delivering 5 watts, doesn't matter where you are. And the 5 watts is spread over a sphere. So that's the knob on the device, okay? So when you adjust it, you're adjusting it to this time of this much of level. So now if you move a meter away, it's going to drop 1 over something meter squared and so on and so forth. So now it's going to be divided by 4 pi r squared. So I want to know, okay, how far r is. So if I use the algebra only, and I need to hear 80 decibels, which is 10 to the power negative 4 watts per meter squared. This must be equal to the I of the source, which is 5 watts divided by 4 pi r squared. Obviously, this expression will give me 5 divided by 4 pi times 10 to the negative 4. And if I do the algebra correctly, so it's going to be 5 divided by 4, which is 1 divided by 3, which is something like 3, okay, times roughly 10 to the power negative, because I borrowed another one, so it's going to be negative 5 or something like that, meters, okay? Oh, I'm sorry, under the square root. Under the square root, okay? So it's about 30 times 10 to the negative 6, which is 10 to the negative 3 meters. So it drops rapidly in this case, okay? I'm not doing the algebra. I count on you guys to check this number. Does everybody understand in here how to find this distance so that the intensity drops by that much? Basically, you want 80 decibels, and 80 decibels in this case is just a comfortable, basically sound, okay, sound level. So if you do the algebra, it's going to amount to about 10 to the negative 4 watts per meter squared, correct? But if the source is broadcasting 5 watts, how far do you need to be from it? Then the 5 watts need to be divided by the area of the sphere, and the area of the sphere is 4 pi r squared, equals to the intensity in watts per meter squared that you need in this case. If you work your algebra correctly, in this case, 5 divided by 4 pi, let's do it correctly, okay? Square root of 5 over 4 pi times 10 negative 4. Come on. Oh man, it did not do the calculation for me. And I don't have mathematics in here. You guys have your calculators available to run this number quickly? Let me know. Came to about 63 meters. Wow. Oh yeah, it's expected. Did I make the conversion wrong? I'm sorry. I made it wrong in there. When I took it to the numerator, hopefully you guys picked up that error, okay? When I took it to the numerator, this should be a positive in here, okay? This should be a positive number. So I made a mistake in there big time. That's why I asked you guys to check the numbers. Sometimes when you're the excitement of getting an idea through, you miss something which is clearly nonsense in here. Actually, and this is also something true for your guys when you're doing your homework and actually doing also your exams, to pay attention to these things in here. When I took 10 to the negative 4 to the numerator, of course I had to, I'm trying to find just an order of magnitude in here. I was not careful enough to put the fact that this is negative power, so when it goes up, it's going to be positive. So it's going to be a very, very big number, not a very small number instead. So it turns out, according to the calculator, about 63 meters. Okay. I want you to check this one also, please. Okay. So that is the item 2. Does it make sense to you guys, though? How to calculate basically distances, intensities, and things like that. This stuff is so far is easy enough. Hopefully you guys can follow it. Yes or no? The reason why I'm emphasizing on that, because this is a typical question in the homework. Okay, very good. So the two main deals of this chapter, okay? The first one is the Doppler effect. And the second one is going to be beats. So for the Doppler effect, imagine the following scenario, okay? And you guys are experiencing it and you know about it all the time. All you have to do is just wait a few minutes until one of these ambulances or emergency vehicles passes by. I live near the hospital, so you're gonna hear that all the time. So here is a source and it's emitting waves. Source can move and its velocity can be Vs in this case, okay? The person who's listening to it is here and can also potentially move. So this is the person listener, a receiver in general, okay? So you don't have to really, it could be a radar from the police officer. That is actually the same thing. But he's sending, in this case, electromagnetic waves, not this kind of waves, not sound waves, but it works with any kind of waves, this phenomenon, okay? This too can be moving. So now we have a situation. Here is the thing. First of all, I'm going to take the case of VL equals to 0. That's easy enough to understand. So the source actually, the listener is not moving. But here is the case. The source sends waves, and the waves are traveling with their velocity v, like we saw, 343 meters per second in normal air, okay? But the source sends a wave and then moves forward toward the observer or toward the listener, okay? So what's going on with the wave fronts now? Here's the deal. Let's take it wavefront at the time. The source sends a wavefront when it was in this location, and the wavefront is here now. Now, later in time, when the source is about to send another wavefront, okay, which is the period in this case. Remember, the source is sending waves every t period, space lambda distance between one another. So if I look at a wavefront and a wavefront, the distance between them is lambda if it was not moving, of course. And the time delay between a wavefront and a wavefront is the period. So that is the how this is working. So it sends a wave, waits t time, which is the period, and then sends another wave. Okay, so the peaks are going to be separated by lambda distance, and also in time they're going to be separated with t time, the period. Okay, so if it was not moving, but here is the problem: after a t time, when it's about to send the second one. So this is the initial, okay? This is the picture we're looking at. The wavefront that was sent from where the source was here, now is here. So this is the one that was sent here. So I'm going to label it 1. So this is where the 1 is. But the source is not in its location where it moved. Here, it moved the distance v source times t and sent the second wavefront. So this is the second wavefront, number 2 now that came out. So the separation between them, instead of being lambda, is going to be this distance between the two wavefronts. Okay? And then it's going to repeat this process after another t time, and then another t time, and then another t time. So for the listener, these wavefronts appear to be separated by a distance, not lambda, but another difference. So for the listener, this is the perception of the waves. They're coming with separation, lambda minus the v source times t. This is the distance between them that the observer is. So for the observer, it perceives a wavelength or a distance between crest and crest, between peaks, if you wish, of lambda minus Vs times t. That is how the observer perceives it. Okay, so that's basically how the observer perceives this separation. Okay, now we have to do some algebra in here to find this stuff in here. Okay, obviously we need to, the t, remember the dispersion law says the v is equal to lambda times t. Okay, and from here we can find this t simply being how should I write it in here? Okay, from the vantage point of the source, it's true. From my vantage point, I know sound travels with a velocity v, but I'm perceiving it at a different wavelength, lambda prime, so I need to really write it as lambda prime times t prime for me. Okay, why did I put lambda times t? It's lambda times f. I'm sorry, lambda times f prime. It's not lambda time, it's not wavelength times time, it's actually wavelength times frequency. Okay, that is the dispersion law that we saw last time for the waves. This is basically, or lambda divided by t if you want to write it that way. Okay, so this is the perceived, because I know that they are separated by a lambda prime. So for me, they sound different because of the fact that this dispersion law is true. For me, I know how sound travels. That's how ear is actually conditioned to the how sound travels in the air. So the velocity should not change. It's the same medium. It should not change at all, unless I go in underwater where the sound is actually perceived differently. So as long as we're conducting this one in the air, this is true for both cases. Now, we're going to use this expression here for lambda and lambda prime, if you wish, and then work out our algebra in here. First of all, t is related to the frequency. T and the frequency are related through one another, like this one. So this expression can be written as lambda is equal to lambda minus Vs divided by the frequency. And the frequency, according to this expression, is simply equal to, I could have written it the same expression, by the way, and I did initially, although it was wrong, as just lambda over t. Okay, so in other words, t also from this expression is equal to v over lambda. Or did I? Yeah, lambda over v, man. Seems like I'm not thinking straight, okay? Lambda over v. Okay, so this expression, the way I calculated myself, the way I see this one, is actually lambda minus Vs times t, and t is equal to lambda over v. So seems like we have enough equations in here to work the expression in terms of lambda. So lambda prime is equal to lambda minus v of the source over v times lambda. Okay, get lambda out as a common factor, which is the way I look at it is how is the source moving with respect to the speed of sound. Okay, the way, again, the dispersion law works in this case is through this expression. So I have an f prime, which is equal to v over lambda prime. Okay, so if I invert this expression enough, I'm going to find 1 over lambda prime is equal to 1 over lambda times 1 minus Vs over v. Okay, and 1 over lambda prime, if I multiply it by, in this case, this expression, which is going to give me 1 over lambda prime is equal to f prime over, oh, I'm sorry, I forgot to invert this one to the -1. Okay, so 1 over lambda prime is going to be f prime over v. So this is f prime over v is equal to f over v for the same reason, times 1 minus Vs over v to the -1, or cancel the v from both sides. F prime is equal to 1 over 1 minus Vs over v times f. This is if the case of, so in other words, we write it sometimes as V over V minus Vs times F. All I have done in this case is just multiply by V, both numerator and denominator of the second half, which gives me the same expression. So in other words, the denominator is clearly less than the numerator. So in this case, the frequency F prime is going to be appearing higher than F. So the pitch is toward higher frequencies in this case because the source is moving toward the observer. Now, if the observer is sitting still, but the source is moving away from him, so in this case, the picture reverses, that's all. In other words, as the source moves in the opposite direction, so instead of perceiving lambda distance, it's going to be lambda plus Vs. So it's going to be a lambda plus Vs in this, Vs times t, of course, because it takes that much time to send the wave. So it's going to be a plus in here, and it's going to be a plus in here, and everywhere there is a minus becomes a plus. So if the source is receding away from the observer, this is the expression that we expect in this case. So it's going to be a plus Vs times F. So this is the source approaching. The first one is approaching. The second one is receding from the observer or the listener. So the frequency is going to be higher in this case because the denominator is less than the numerator. The frequency is going to be less in this case because the denominator is bigger than the numerator. Okay, that is if the observer is actually sitting still and the source is moving. If, on the other hand, the observer is actually moving and the source is not moving. So the source is sitting in here and sending wave fronts after the other at separated by lambda distance between one another and at time intervals of t between one another. And then the source, the observer now, or the listener, is moving with a VL. Because this distance is fixed now, lambda, between wavefront and wavefront, the observer will find them because he's moving toward them, okay? And will encounter them in less and less time because normally it takes t time between each and every one of those wavefronts. But he's moving in the same direction. So he's going to reduce the time where he's going to encounter them. So the distance is fixed in this case. The only thing that is different is the time that he's going to measure with his ear, that he's going to pick up with the ear. So it's going to be the time t prime again is going to be distance divided by velocity. And the velocity in this case is just the relative velocity between the two. So the waves are moving in this case with v, and he's moving in this case with the velocity vl. But it's going to be the algebraic difference, which is the sum. It's like two cars. One car is coming at 50 miles per hour, and the other car is going to it by 50 miles per hour. So how fast this car is approaching the other one, relatively speaking, it's going to be 100 miles per hour. Because you're sitting in your car, as far as your car, yes, your car is on cruise control, going 50 miles forward, but the other one is coming 50 miles forward from the external observer. For you sitting in the car, it looks like the other car is going to come at 100 miles per hour. If you're going in the same direction, 50 miles per hour, and the other one is 50 miles per hour, then in this case, it's clearly the difference between the two, 50 minus 50 is 0. And actually, you can talk to one another. So it's actually the relative velocity, but it's an algebraic expression. So in this case, the velocity is going to be the sum of the velocities times, in this case, the distance lambda, the distance divided by velocity. Again, the distance lambda, if I express in terms of, I can leave it in terms of time in here, okay? In terms of how should I put it? In terms of distance, lambda, the way I perceive it then is the wavelengths are not really lambda, but there looks like it's lambda prime over v, okay? Again, if I work out my algebra for lambda prime times v in this case, so lambda prime is going to be v over v plus vl times lambda. That's the wavelength. If I express the same expression, if I invert everything correctly, 1 over lambda prime is going to be v plus vl over v times 1 over lambda. And again, I do the same trick as I did earlier before in here when I did the inversion in here, and use replace the 1 over lambda prime by f prime, because again, the dispersion law is still true for either case, for the perceived or the real, okay? So it's 1 over lambda prime in this case is going to be equal to f prime over the velocity of sound. So this is f prime over the velocity of sound is equal to v plus vl over v times, again, the real one is f over v, cancel the v from both sides, and the f prime in this case is going to be v over vl over v times f. Again, this is the perceived frequency is going to be higher and higher as the source is sitting still and you're moving towards it. So in this case, it looks like the frequency is getting higher and higher. If I do the same algebra and think of the observer moving away from it. So the wavefronts are still, in this case, this way, but as if two cars are moving in the same direction. Namely, the sound is moving this way, and the observer is moving this way. So the relative velocity in this case is going to be simply v minus vl. If the two are moving in the same direction, speed, they're not going to gain or lose any speed against one another. So again, this is the signs where they were positive, they become negative, because the relative velocity is always the difference. The only reason why we added it the first time is because of the algebraic sign. Minus minus is going to be positive. And the only reason why we have a minus in here where we're supposed to add is because, again, we're adding algebraic, we're subtracting algebraic values in this case, and we ended up with a plus. We're subtracting algebraic values in this case, and both of them are positive. So it's going to be minus in this case. So if it is receding, f prime is going to be less, actually, v minus vl over v times f. Again, here the observer or listener is approaching the source, in which case the frequency is higher because the numerator is greater than the denominator. In the case when it's receding from the source, the frequency is going to be lower because the numerator is less than the denominator, okay? So again, we write these expressions as follows, and hopefully summarizes everything for you guys. It's going to be V, and it's going to be VL in the numerator. It's going to be V, and it's going to be the source in the denominator, where V is the speed of the wave. And F in this case. I need to decide on the size. If the observer is approaching, it's a plus. If the observer is receding, it's going to be a minus. If the source is approaching, it's going to be a minus. If the source is receding, it's going to be a plus. So in here, the plus is approach, closer. The negative is recede. Here, it's approach. Here, it's recede. Okay? The numerator is listener. The denominator is source. I don't mean V. V is the same thing. V is the speed of sound, the speed of the wave. Basically, the numerator describes the listener, what the listener is doing. If the listener is not moving, then there is no plus or minus. It's just V. The same thing with the denominator. If the source is not moving, there is nothing in the denominator except V. Okay? Which sign I need to take? If they're approaching, the sign above. Whether the numerator or denominator, doesn't matter. So the signs are flip order in a little bit. If they're receding, I use the second sign on the bottom. And the argument for it is up there. Make sense? This summarizes everything for the Doppler effect. Important. A lot of the homework problems and exam problems rely on this, just understanding this, how to use this expression. Make sense? It's okay if it's not clear to you guys, please let me know, okay? Obviously, we're going to do examples and hopefully it becomes clearer as we do them. Yes? Good. Okay, very good. Thank you, Micah. Okay. Here is an interesting case, and that is shock waves. When you have a source moving with a velocity higher than the speed of sound. So in other words, Vs is bigger than V of sound. Here is the situation. You have the source sending a wave and then moves away here and sends the second wave front. Obviously, the second wave front did not even reach that point. The source has reached it, okay? So this is where the wave front is. The second wave front already on the way, okay? By the time it's in this point in here, it's gonna send the second wave front where the third wave front where this first one is still here. And the first one is probably here. And so on and so forth. You can clearly see in this point in here, for example, the wave that starts to pile up. There is this one from the beginning, the first one, and the second one, okay? If I continue with this analysis because sound is actually coming with very high frequency most of the time, so this picture is really not that good. So this is how it looks like now. It looks like the source, which is usually an airplane that is supersonic, because again, the speed is V of the source is higher than the V of sound. So in this case, here is how the picture looks. So by the time the plane is in here, I would have accumulated enough basically of this for an observer sitting in here. So this is the listener. Is going to pick up an accumulated number of wave fronts, which is going to be higher and higher as this wave front is moving in here, so that the original sound for him to hear traveled a certain velocity of sound times the time it took for it to come from here. That depends on the distance, how far the plane is. And then he sees the plane in the same time travel this distance, Vs times t. He looks at the sound and how they're piling up. They pile up in a cone in such a way that this angle of the cone alpha, okay, that's for the conic shape that forms, is this angle is because, again, the cone is a spherical shape, actually a spherical shape, yes, at least the projection is going to be a bunch of circles. The tangent of this is actually forms a 90-degree angle in this triangle, because again, the tangent to a circle is always perpendicular to it. So this is a 90-degree angle. The angle alpha in this case satisfies the condition that tangent of alpha is equal to, this is the hypotenuse, so it's going to be a sine of alpha is going to be the opposite, which is in this case the V of sound times the time it takes to reach the observer divided by the velocity of the source where the plane is in the same time. Cancel the time, it doesn't matter what it is. So it's the ratio of these two velocities. Again, that uses the shock waves. This is the supersonic, and that's the sonic boom that you guys have seen. This has a lot of applications. One of them is the Cherenkov effect that occurs in nuclear reactors. For light, actually, it's a similar effect that we observe. And I think for physics too, for those sitting in physics too, we're going to talk about the Cherenkov effect when we comes time to it. Or probably we're going to discuss it later in optics, okay? But this is the sonic boom. Because there is a pileup sonic, it's only one O, boom. There are two O's now, okay? Because there is a pileup of waves, and when they hit your ear, they come up with so many wave fronts with a lot of energy that yank your ear out because it's the rarefication and push it backward. You hear a super loud sound, actually, because the plane is moving faster than sound. It passes by before you actually see it, okay? Make sense? The key relationship in here is this one, the sine of alpha, the shape basically of the sonic boom is the ratio of these two velocities. Remember, v is less than vs, meaning the source in this case is moving faster than the speed of sound. So you can see that, okay? You can see the sonic boom forming. I mean, you cannot do it for light, at least for the plane, because light, nobody can travel faster than light, but at least for sound you can. Make sense? Good. Can we move on to beats now? Come on, guys. Where's my... Oh, I can see what's going on. Because when I am sharing the screen, I can't see much. Makes sense good for you guys? I'm relying on you to go through the lecture, read the notes, read the summary also to emphasize on what is important for this class, because you're going to be having a quiz on every chapter, so you're supposed to understand everything in there. And also, if you have any questions, please do ask them. Do not let things linger like this, and or anyway. Can we move on to beats now? Okay, very good. Thank you. So again, here is a scenario, okay? I have a wave source that is emitting a wave. I'm going to write the wave in here in general. It doesn't matter what it is. It's going to be sound. I'm going to express it with y equal to some amplitude times a cosine of some wave number minus omega t. Again, k and omega are related to one another in such a way that omega equals to kv, where v is the velocity of sound. So this is what we described before as the, for the case of the string, and it works also the same thing for sound too in this case. So this is the angular frequency. And this is the wave number. Remember, omega is related to the frequency via this number. That's the actual frequency. And k and the wavelength are related to another via this expression, okay? So this is a convenient way of writing the wave. So we have a source now, and it's giving me this wave. I'm going to call this one source 1. I'm going to have another source now, source 2. And it's giving me actually another wave of the same amplitude, A. So this is A is the amplitude. So more or less the same intensity of sound, or whatever wave we're talking about in here. Cosine, again, of kx minus omega t. I have to be careful with these omegas in here in this case. So probably this one is an omega 1. This is an omega 2. This is a k2. This is a k1. K1 and K2 will not matter, and I will tell you exactly why. Because I am a listener listening to these waves, and I am situated at specific points in space. I'm here. And this is the source S1, and this is the source S2, okay? As they send their waves in here and they reach me, I'm in the same location. I could take that location to be 0. I could take x equal to 0. If I take x to 0 equal to 0, the spatial behavior will not matter because k1 times 0 and k2 times 0 is 0. You say, well, how about if you don't take it 0? Well, that's fine. We can take it not 0, okay? We can take x not equal to 0. So this number is going to be constant then, because I'm not moving. I'm stationary. So the listener in this case is stationary. Just listening to sound, okay? How it came, but coming from two different sources. Obviously, what matters in this case is the time delay. That's all. Is this times in here, okay? But I'm sitting in the same place listening to them, so the time is going to be the same. So what is going to be different is the frequency in here that is going to be different, because this difference is just going to be a number. And I'm listening to the sound, how it changes with time, how it goes up and down, okay? I'm listening to the frequency. So yes, the time is going to be drifting. I'm looking at the clock, and I'm going to record that. So this is going to be just a shift in the phase. Okay, shift in the angle, if you wish, that's all. And what is t equal to 0 for me? I can shift my t equal to 0 enough so to disregard the clock, so that when I click on exactly when the time starts, that is basically what that means. So it's just an angle, because I'm not changing location. If I am changing location and I'm trying to see how sound is sounding in different places, then x will become important. Otherwise, now it's not. So we're either take it equal to 0 and it's the same point, or leave it constant, and it's going to do is shift your coordinates. For me, the wave that is coming is just a combination of the two waves, because the wave equation is a linear equation. So if I add two waves, it's actually a wave. So for me, y is equal to a cosine of k1 x1, and this number is fixed, minus omega t 1t, where t changes with time, plus a times cosine of, again, k2 x2 x1, because it's the same number in here, okay? So the x is fixed, minus omega 2t, okay? This number x is just a fixed number, so I could take it equal to 0 from the get-go and simplify the headache that is going to arise from it. The only thing is going to change the angle, that's all, okay? So k1 times x is fixed, times x1, I should say, is fixed. It's not changing with time, at least. And k2 times x1 is the same thing as fixed. And at the end, probably I will have their sum or difference, which is not going to matter much, because all I'm doing is shifting the phases, that's all, the time, that's all, okay? I could take x1 equal to 0 and be done with it. If I take x1 equal to 0, that solves my problems from the get-go and simplifies the algebra. Does this make sense? If you guys are not happy with this argument, leave x1 not equal to 0. You can leave x1 if you like, okay? And then work with it. And it's going to really all it does is shift just the discussion a little one way or the other, meaning when do you consider t equal to 0, that's all, okay? When do you consider the start of time, that's all, in the argument. Because you're sitting in the same place and listening to two sounds, okay? The way your ear is moving back and forth, that is what matters for your brain in terms of perception of sound in this case. You're not moving toward the source or away from the source. Make sense? So I'm going to take x1 equal to 0 just to make the algebra easy on me, okay? To make the discussion easy, okay? So for x1 equals to 0, that means I'm calculating distances from that point on, okay? Then y is simply y1 plus y2 in this case is going to be cosine of omega 1t plus a sine of, cosine of omega 2t. Where omega 2 and omega 1 are two different frequencies for two different sounds, okay? Okay, so they have two sources. They don't necessarily have to emit in the same frequency. One of them could be a low pitch, the other one high pitch, doesn't matter. So now I have to do this algebra in here. A is equal to A times the cosine of omega 1t plus cosine of omega 2t in parentheses. I took the A out, by the way, okay? Here is something that I know from trig identities. I know that cosine of an, I probably need to use the Greek letters again. Cosine of alpha minus beta is equal to cosine of alpha cosine of beta, and a cosine, minus sine of alpha sine of beta, and also cosine of alpha plus beta. Oh, I'm sorry, this is plus. I forgot my trig identities again. It's cosine of alpha cosine of beta minus, so when it's a plus, it's a minus actually in the trig identity, sine of alpha, sine of beta, okay? So if I do cosine of alpha plus beta plus cosine of alpha minus beta, I'm trying to get some identities in here. It's gonna be If I add this 2, it's going to be just twice this one because this signs will cancel. So if I add them side by side, it's going to be twice cosine of alpha, cosine of beta. This is another trig identity that probably is worth remembering, but I can derive it easily from this trig identity. Now, if I choose my alpha and beta in such a way that alpha plus beta is u, and alpha minus beta is w, clear from this expression in here that I will have a cosine of u plus a cosine of w. I need to express this one in terms of u and w. From this expression, alpha plus alpha is 2 alpha, beta minus beta is 0, so it's going to be just the sum of u plus w. So alpha itself is just the sum of the two numbers divided by 2. So it's going to be just u plus w over 2. And cosine of beta, beta itself is going to be the difference because alpha minus alpha is 0, beta minus beta is 2 beta. Is going to be u minus w. So again, it's just cosine of u minus w over 2. This is the expression I wanted. I wanted the cos plus cos. What in the world is that? Since I already have a cos plus cos in this case. So it's going to be 2 times a, because I have an a in front, times cosine of the sum divided by 2, times cosine of the difference divided by 2. So y, the way my ear perceive it, is going to be like this. Y is going to be 2a times a cosine of the sum divided by 2, which is omega 1 plus omega 2 times t, times cosine of the difference between the two frequencies, omega 1 minus omega 2 over 2 times t. Okay, so that's how my ear will perceive the sound in this case. Okay, now this is all well and done if omega 1 is different from omega 2, but what if omega 1 is very close from omega 2 but not equal to? In other words, omega 1 is equal to omega 2 plus some delta omega. Okay, small difference. Obviously, omega 1 plus omega 2 over 2 is going to be equal to, first of all, 2 omega 2 plus delta omega over 2, which is roughly omega 2 plus delta omega over 2, which is 0, which is small, okay? And omega 1 is roughly equal to omega 2. So this is actually equal to, almost equal to omega 1 too, because the difference between them is slightly. So this term will be exactly like one of them, because both of them are coming with either omega 1 or omega 2, and those two are close from one another. So for my ear, I will perceive both of them as being through that factor as if that's out. However, there is another component on the other side that is going to change things a little. And that is the difference between them. And the difference between them is exactly delta omega, the difference between the two angular velocities. So this is how y I'm going to perceive it. It's going to be 2 times cosine, 2 times a, I'm sorry, times cosine of the difference, and cosine of the difference divided by 2 is delta omega divided by 2, times t, cosine of the sum divided by 2, which is either one, pick and choose. Both of them are close from one another anyway, okay? So that's how my ear will perceive it. It's going to perceive the main sound, which is both of them. But its amplitude is changing. The amplitude of sound is not constant. It's this number. Okay, that's what is different. Okay, so I know we did the simulation in GeoGebra the other day. So let's redraw this thing in here and see how it looks like in time. Okay. For my ear, it's going to perceive the main frequency, which is usually a high frequency. So it's going to receive this main frequency. I'm going to use a cosine, so we use a cosine. But its amplitude is not constant. So this is if it were a constant amplitude. The envelope for it, that's what its term is in front of the cosine is called actually, is also a periodic function, and whose periodicity in this case looks like, at least it looks like, and you have to be very careful with this looks like, because I'm going to tell you exactly what it looks like. It's going to look like 2 pi divided by this number. So it's going to be looking 2 pi divided by this number, which is delta omega times 2. So it's going to look like it's 4 pi divided by delta omega. Delta omega being small, that means the period t is going to be very long because delta omega is tiny, okay? The difference between the two frequencies is small. So that means the t is large. The period is large, meaning I'm going to hear the sound, the main sound, this one, but changing over a long period of time, depending on that delta omega, how small delta omega is. So this is how actually it's going to look like. It's going to be a sound that is periodic, but then it's going to start to shrink, and then periodic again, and then it's going to start to shrink, and then probably it's going to be in here too, and then it's going to shrink, and so on and so forth. So this is the t I was talking about. This is the 4 pi over t. Actually, this is, I'm sorry, this is half of it. This is just the 2 pi over t. Because look, 2 pi over t. I'm sorry, this is the time t, yes, okay? But it's actually over twice this many, because half of which is going to go up and down, and the other half is going to be up and down for a full wavelength. But for me, my ear will actually listen to only half of it repeating. Because if I square this number, to get the power, because it's proportional to omega squared, my ear cares only about the intensity, which is omega squared in this case. So it's going to hear high, then it starts to go down, then it's going to go higher again for high frequency, and then come down. And the high frequency is the omega itself, which is either 1, they are very close. But that often, how often it's going to go is going to be just the delta omega in this case. So the period t, the actual perceived period, is going to be half that period because of this parameter. It's going to be just 2 pi over delta omega, which means the actual frequency in this case of the beats, angular frequency, if you like, angular frequency of the beats is omega 1 minus omega 2. And if you convert it to frequency, all you have to do is just multiply by 2 pi everywhere, or divide by 2 pi everywhere. So the f of beats is just the difference in frequencies, f1 minus f2. Okay, this is the angular difference between them. Okay, so this is the angular frequency. So just multiply. This is 2 pi times f1, 2 pi times f1, and this is 2 pi times f beats. Okay, so that's basically 2 pi cancels everywhere, and now this is the frequency of the beats. In other words, if the two sources are exactly equal to frequency, you are not going to hear that difference. If the difference between the delta omega is equal to 0, the two frequencies actually have the same exact value. That means their t is equal to infinity. That means they will repeat after an infinite amount of time, which means they don't repeat. So that means you're going to hear either one the same way. Okay, and you say in this case, I have perceived an actual tune. The two frequencies are actually in tune with one another. They are actually synced with one another. But if there is a slight difference, you're going to hear that beat, okay? But if there is a big difference, you're going to hear the first frequency, the second frequency. As a matter of fact, you're going to hear a hum still between them. You're going to hear 3 frequencies if there is a big difference between them, because that difference will come into play too. So if delta omega is big, in other words, you're going to still hear the two frequencies, omega 1 and omega 2, but you're going to hear also the difference between them, in this case, spanning over, because delta omega is big, that means t is going to be smaller in this case, okay? You're going to hear that distinction between the 3 frequencies in this case. Anyway, this is your beats in this case, okay? So for delta omega is big, t is less, so it's going to repeat, but you're not going to be noticing much. So when there's clear distinction between the two of them, when delta omega is very, very infinite in this case, you're not going to hear the sound at all difference between them. So this is basically what the beats is. It's used for piano tuning. It's used for tuning instruments. It's used also for in industry. You have to avoid something like this because it could be damaging to your instruments. Like for example, in a plane, for example, with 2 engine planes, you have the propellers, both of them going and humming and doing all kinds of motion. So in this case, it could lead to interference, which could lead to problems for the propeller. So this is something that you have to really have in sync to avoid any problems. And you actually hear it sometimes in your car when there is a problem, probably the timing belt or some of the issues there and the different moving parts where you're going to hear a hum. In this case, there is something that is not in sync. If you're careful enough, you're going to be listening. So experienced drivers usually have a feel for their cars or vehicles because they can listen to them. Okay, this is the entire chapter in its entirety, covered everything that needs to be covered in this chapter. And I'm waiting for you guys to do the lab later on this afternoon on standing waves, which is a fun lab. So I'm hoping that you guys will enjoy it. And then we will meet on Wednesday specifically for doing problems from this chapter. I think I'm not sure if I said the 100% or some of them, but I'm still. You will have definitely problems on the Doppler effect, as I said before, because those problems are typical problems from this chapter, and they have a lot of applications. So we will have problems. So here's the deal. In the lab this afternoon, I'm going to talk about the problems because I'm still debating some of them. And some of them probably are going to be on beats, and that's going to be Wednesday, okay? So for those sitting in physics for B, the Monday session, we'll see you today. Those in physics for B in the Tuesday session, I'll see you tomorrow. For all of you guys, I'll see you this afternoon for the lab. Good? So I'm going to stop the recording.